Solution stoichiometry. So molarity relates moles of solute to liters of solution, and so we can use this to measure our reactants as volumes of solutions instead of as masses. So molarity is useful in the same way that molar mass is useful. So we said that for stoichiometry, we have grams to moles to grams. Well, if you've got solid reactants and solid products, then we definitely want to do that grams to moles to grams. But what if your solute is dissolved in water, in a solution? It's more convenient to measure the volume of a solution than try to measure the mass of a solution. So if we have the volume of the solution, we can convert that to moles using the molarity. So the molarity is the conversion factor here. When we did grams to moles, it was the molar mass. The moles to moles in the middle is still the mole ratio, and then again at the end, to go to volume, we'll use molarity. So this is still our starting point, grams to grams, but sometimes we recognize, no, I don't want grams at the end, I want volume. So we can just switch up the ends. The middle is always the same. There are always moles in the middle. Remember that show, Malcolm in the Middle? There's moles in the middle. So moles in the middle, and that can help you if you're having a hard time figuring out, how can I get from one place to another? You know, I've got grams of this and I've got a volume of that. How do I convert those? Maybe moles in the middle is what you usually need to do. So let's do a problem here. What volume in milliliters of 0.15 molar HNO3 solution will completely react with 35.7 milliliters of a 0.108 molar Na2CO3 solution according to the following balanced chemical equation? So, as I did with the mass stoichiometry problems, I'm going to use my chemical equation to organize the information. So here I've got a concentration of HNO3. I'm going to write that under HNO3 in the balanced chemical equation. So 0.150, I'm not going to write capital M, I'm going to write moles per liter. That's what the capital M stands for. A very common mistake is that students think the capital M is an abbreviation for mole. MOL is the abbreviation for mole, MOLE, right? The capital M is not another abbreviation for mole. Capital M is moles per liter. And then I've got 35.7 milliliters of this Na2CO3 solution, so 35.7 milliliters. And they give me the concentration of that, 0.108 moles per liter. What am I trying to find? Whoops. Volume in milliliters of HNO3. So my question is, how many milliliters of that? So this is stoichiometry. This is not dilution. In dilution, you have one substance and you're adding solvent. Here we have two different substances, two different chemicals. Don't use the dilution equation, okay? You may run into a tutor that says, oh, you can use that here. Say, no, Mrs. K told me not to do that. Go away, take your garlic or something with you, right? Don't do it. The danger of using M1V1 for stoichiometry is that under certain circumstances it works, but a lot of times it doesn't. And guess what kind of problem I'm going to give you on the exam? The one that doesn't work. So M1V1 is not going to work for stoichiometry on the exam. So just don't ever use it that way, okay? okay? This is stoichiometry. It's a variation of grams to moles to moles to grams. That's all it is. So let's think about this. We're doing stoichiometry. We have a chemical reaction, and we've got amounts of stuff. So we start with grams to moles to moles to grams. Do we have grams of anything? No. Well, this is the thing that we know more about, right? So this is the thing we're starting with, but what we know about it is milliliters. So this is milliliters, and is milliliters of the sodium carbonate. Can we get from milliliters to moles? Yeah, we can. We might need to use liters in there, but this relates volume to moles. So this is going to be our conversion from milliliters into moles. Moles to moles in the middle, stoichiometry, the coefficients here. We'll get moles of the other thing, which is the HNO3. And do we want grams of that? No, it says we want milliliters of that. So here we're switching at both ends. Any questions?
So it's okay if you only switch one end? Sometimes?
Yes, sometimes you only switch one end. They might say this many grams and ask you for volume at the end. Or they might give you volume at the beginning and ask for grams at the end. And then, as we go on, we're going to add a couple of other ways to do it, to change it up on the ends. So milliliters to moles to moles to milliliters. So let's just start out and see how that goes. So 35.7 milliliters. And now it's important to say milliliters of what? Because we've got two different things here. So this is milliliters of that Na2CO3 solution. And my path says I'm going to moles of that. And then I'm going to go to moles of the other thing. And then I want to go to milliliters of the other thing. We've got the same issue here that we did when we had kilograms to moles to kilograms. And I probably confused you by showing you too many ways to deal with that. Does anyone have a strong opinion of how they prefer to deal with it?
Since it's the same on both ends, we just use the regular ones, right?
Yes, since it's the same on both ends, there's a milliliter here and a milliliter here. We can actually do the problem without converting to liters, and the millis will take care of themselves. So let's do it this way. I'm going to write the milli in red. I'm just setting the milli aside, and I'm not going to worry about it. And I'm going to convert the liters of sodium carbonate. So my unit down here is going to be liters of sodium carbonate. Accidentally switched purples, oh well. So those cancel out. And moles of sodium carbonate. Whoops. Cancel out. And moles of HNO3 cancel out. But again, I'm going to put this milli in red. So we're just ignoring the milli for now. Well, what's the relationship between moles and liters of sodium carbonate solution? It's 0.108. This number goes with moles, and liter is on the other side. So it's 0.108 moles per liter. If it bothers you that there's no number down there, it would be per 1 mole. I'm sorry, per 1 liter.
Where would you use the 0.108 on the bottom?
Well, we'll find out that here, this one ends up being on the bottom. So this other one, we've got moles in the bottom, liters on top. I didn't leave enough room, of course. 0.150 moles per liter. And I'm just actually going to physically lift out those M's. So I've got liters to moles to moles to liters. And in the middle, my moles in the middle are the coefficients here. 1 mole of sodium carbonate, 2 moles of HNO3. So 1 mole of sodium carbonate, 2 moles of HNO3. Everybody okay with that? So if I do the math, 35.7 times 0.108 times 2 divided by 0.150 equals, this is going to give me 51.408 liters. Oops. Now put the millis back. I should have 3 sig figs, and so my answer is going to be 51.4 milliliters of HNO3. Any questions? The thing about the milliliters, unlike kilograms, the milliliters, we're almost always going to have the volumes in milliliters because it's a more useful unit for real life sized things. And so we need to learn how to deal with them. I want to show you something else here. If I take this molarity, 0.108 moles per liter. So that is true. 0.108 moles is equal to 1 liter of solution, right? If I put a milli on the top and a milli on the bottom, does it change the fraction? No. This is like taking the top and multiplying it by 10 to the minus 3 and taking the bottom and multiplying it by 10 to the minus 3. If I do the same thing to the top and bottom of a fraction, it's still the same fraction, right? Well, so I could use this in my equation and I would have my milliliters cancel out. So millimoles are really useful, but they confuse students as well, so. 51.4 milliliters. Consider this reaction. This one's conceptual. What is the limiting reactant if you mix equal volumes of a 1 molar solution of A and a 1 molar solution of B? So this is pulling limiting reactant ideas from the previous chapter. So this equation, what's the equation telling me? I need how many moles of A? I need 2 moles of A for every 1 mole of B. I need twice as many moles of A, right? If I have equal volumes and the solutions are equal in concentration, then I have an equal number of moles, right? So which one am I going to run out of? Not B. C. A. I'm going to run out of A. So it says equal volumes. So sometimes problems like this, they're conceptual. They're thinking about the concepts, the big ideas. And we get so accustomed to solving problems that when we have a question like this without the numbers needed to solve it, we have a hard time with it. Well, sometimes what you can do is you can make up numbers and actually do a calculation even though you don't need to do a calculation because your brain might think that way better. So it says equal volumes. Well, what would be easy? 1 liter of each, right? So if I had 1 liter of solution A and it's 1 mole of A per 1 liter, how many moles of A do I have? I have 1 mole of A. Well, I'm not looking at the reaction here. I'm saying if I have 1 liter of this solution, I have 1 mole of A. And if I have 1 liter of solution B, and its concentration is 1 mole per liter, then I have 1 mole of B, right? So this is like 2 dozen shoes and a dozen people, right? Each person needs 2 shoes, but I have a dozen shoes and a dozen people. What am I going to run out of? I'm going to run out of shoes, right? Only half the people are going to get shoes on both feet. For every 1 mole of B, I need 2 moles of A. But for every 1 mole of B, I have 1 mole of A. I'm going to run out of A before I run out of B. Okay? No? You don't get it still? Okay, so we can take this and say, well, to react my mole of A, how much B do I need? So I have 1 mole of A, and I'm going to figure out, well, how many moles of B do I need to react with that? Well, the coefficients tell me I need 1 mole of B for every 2 moles of A. Should have done it the other way. So this is going to give me half a mole of B. So do I have enough B to react with the A? To react with all the 1 mole of A, I need half a mole of B. I have half a mole of B. I have a whole mole of B. What's going to get left over? Let me do this the other way.
What's throwing me off is that it's the limiting reactants of least amount of the product, but there's 2 in it. So how is that one diluted with 10?
So let's do it this way. Oops. That's not what I wanted to do. Oh my goodness. Disaster here. Okay, so limiting reactants, we took the amount of product and we calculated the amount of reactants. So let's do that. I have 1 mole of A, and I'm going to calculate how many moles of C, how many moles of product I can make. Well, I get 1 mole of C for every 2 moles of A. And so I'm going to get 0.5 moles of C when I use up all of the A. And then I'm going to calculate with my other one. I get 1 mole of C for every 1 mole of B. So if I use up all of the B, I can make 1 mole of C. So when I've made half a mole of product, I've used up all of my A. Reaction stops. This is my limiting reactant. Multiple ways to think about it. Anybody else need another way to think about it? I think I could come up with one or two.